Hello, Comets. Welcome to Peer Tutoring for Math and Science. I am your host today, Kevin, and today we're going to be talking about the kinetics of radioactive decay. So what is radioactive decay? It's basically the loss of elementary particles like protons or electrons or neutrons from an atom with an unstable nucleus, which forces it to change into a different element in order to gain stability. So I have here a general equation, A yields B, C, and D, where A is the unstable atom breaking apart into B, which would be a different element, and then C and D are different elementary particles that could be lost. So it's been discovered that the rate at which this radioactive decay can occur can be modeled by first-order reactions. So using what we can know about the kinetics from first-order equations, we can solve for radioactive decay rate constants, any concentrations, and even half-lives. So if you guys remember from our first-order kinetic equations, we have ln of A over A naught is equal to negative KT. And the second one, rearranged here, is just another way of writing that. So A is the amount of isotope that is left over after T has elapsed, and A naught is the initial amount of that radioisotope, and K is the rate constant. So the units for A, they can be either mass or moles or even atoms. As long as they stay consistent, you can have either type. And the units for time will really depend on the units for the rate constant. As long as your time and rate constant are the same, they are either in minutes and per minutes for the rate constant, or seconds and per seconds for the rate constant. But also the half-life of the reaction is the time that is needed for the reactant concentration to decrease to half of what it used to be. And for first-order reactions, the half-life formula ends up being T half-life equals ln of 2 divided by K, the rate constant. Okay, so let's go ahead and do some practice problems. Okay, so looking at this one, we're looking at how much of a 2-gram sample of radioisotope, where K is equal to 0.15 per minute, will be left after about 20 minutes. All right, so let's go ahead and solve that. So let's go ahead and use that first-order kinetic equation we have. Ln of A divided by A naught is equal to negative KT. Okay, so we're looking for how much remains, right? So that means we're going to be looking for A. So let's go ahead and rearrange this equation for A. Okay, let's take both sides to the power of E. So that means we're left with A over A naught is going to be equal to E to the negative KT. That's good. All right, and then go ahead and bring that A naught over times E to the negative KT. All right, so now A naught, what was that original concentration or amount? It's 2 grams. So let's put 2 grams times E to the negative, what was our rate constant? 0.15. 0.15 minutes per minute, sorry, times 20 minutes. So what does that end up being? So you'll end up getting 1.48 grams, which is less than 2, which is exactly what we're kind of looking for. Remember, radioactive decay, you're going to have less. If you somehow end up with more than you started with, then you should go back and double check your work. Well, let's move on to the next one. Okay. All right, so we're looking at determinations of the rate constant. So basically, we're looking for K. So for our sample here, we have a sample that is 70% as active after 20 hours have elapsed. All right, 70% active. So determine the value of the rate constant. So we're looking for K. Okay, so again, let's use that first order kinetic equation. Ln of A over A naught is equal to negative KT. All right, and let's go ahead and rearrange for K. That's what we're really solving for. K is going to be equal to negative ln of A over A naught all over T. All right, cool. Okay, so since he said our sample was 70% as active as previously, we basically can choose any number as long as for our A naught, as long as our A is 70% of that. So to make our life easy, let's go ahead and say that A naught is 100, right? And so what is 70% of 100? It's 70. All right, let's go ahead and fill in our values here. 70 over 100. And again, the A and A naught can be grams or moles or molarity. It doesn't matter as long as the units are the same. And over our time, which is going to be 20 hours. Okay, so if you throw that into your calculator, you should get 0.018. And what's the units? It's going to be per hours because our time here was in hours. So make sure our rate constant agrees with that. Awesome. All right, and let's do one last example. Determination and use of the half-life formula. All right, so it says how much of a 20-gram sample of radioisotope will be left after 10 minutes if the half-life of the radioisotope is 2.75 minutes. Okay, so let's go ahead and write out what we know. We have A naught is equal to 60 grams. Looks like we're looking for how much is left over, right? So we're solving for A. It looks like our time here is going to be 10 minutes. And our half-life, T1/2, is going to be 2.75 minutes. All right, we don't know what K is, right? We're not given a K. So that's what we're going to solve for. So let's go ahead and do that. Remember the half-life formula? I'll write it out. Equals ln of 2 over K. So notice it's a positive ln of 2 over K. So we know what our half-life is. We know what ln of 2 is. It's a constant. We can throw that in a calculator. And we can go ahead and solve for K. It's going to help us out to know that. So K is going to be equal to ln of 2 all over T of 1/2. All right, so let's go find that. ln of 2 over 2.75 minutes. Okay, so we end up getting K to be, if you guys want to work that with me, 0.252 per minute. Again, the units have to agree. All right, so now we have what K is. Let's go ahead and use that first order kinetic equation. Let's get pretty straightforward. It's going to be your best friend, this one equation. Okay, so again, we're looking for A, right? So let's go ahead and rearrange that equation for A. So take everything to the power of E to get rid of that ln. A is going to be equal to A naught times E to the negative KT. A naught was 60 grams, right? Times E to the negative 0.252 per minute. Then times 10 minutes. All right. And if we check that in the calculator, that ends up giving us 4.8 grams is left over. So basically, that's how we can solve our first order kinetics of radioactive decay type problems. If you guys need any help or assistance, please drop by at Peer Tutor. Thank you.